I will be solving some of the in-chapter problem of advanced electromagnetic book of Belanis. And before getting started, I would like to present my screen. Yeah, today I'm going to be covering chapter 4 and chapter 5 of the end chapter problem, some of the selected problems. And let me quickly present my screen. Now, you should be able to see my screen now. So I'm going to be choosing from question 4.8, 10, 15, etc. They are represented from this book. There's the book of Belanis. And then you can actually open the book to follow my concepts. Before starting, I would like to give a short summary of the entire chapter so that it can be carried along, and then to explain each of the formula that we're going to be using in this problem. So chapter 4, it first starts with wave propagation, and then that's the movement of electromagnetic wave from one medium to the other. Then it's divided into two, which is known as the normal incidence and then the oblique incidence. So from the normal incidence, we are going to be treating the electric field, where we are going to be explaining the actual formula for the expression for electric field measured in volt per meter. And then we are going to also explain what we know as the magnetic field. Then the electric field in a normal incident, that is, of course, when it is moving in the principal axis alone. It does not have X, Y, Z, as the only one, the wave is moving in only one axis. So now the E is going to be the magnitude of the E, and then the E raised by minus J with a Z, where beta is our propagation constant, and then the Z is the direction of propagation. So the magnetic field can actually be calculated from E when our E is known either by the use of the right hand rule, or by using the common formula, which is the K cross E over the N, where N is the impedance, the wave impedance, and then the K is the what is the unit vector of the wave. In this case, the Z, that it means the unit vector is the AC. So that's that about H. The next one is the beta, not actually B. B is a magnetic flux density. Here I'm gonna write beta. And then the beta does as I said. So it before the propagation direction is written like C. You first write the beta, which like the wave number, which states like the magnitude of the beta. So that is 2 pi, and then it's otherwise known as K. That is 2 pi over lambda. Lambda is the wavelength, depending on the medium of concentration. If we are considering air, definitely our lambda is going to be lambda naught. And then that can be calculated from C is equals to F lambda, where C is the speed of light, which is 3 times 10 raised to the power 8 meters per second. And then the F is the frequency, where our lambda is the wavelength measured in meter. The next one is the wave impedance, which is the like eta. So the wave impedance, of course, it's otherwise the wave impedance, of course, it is measured in ohm rather, where we have the phase velocity as well. The phase velocity, that is of course just like the velocity, the movement of wave, and then it is omega over beta. So the epsilon r, which is the relative permittivity, it's of course a constituted parameter of the material. It depends on the material under consideration, of course, and we already know that the absolute permittivity, that is epsilon naught epsilon r, that is the permittivity of free space multiplied by the epsilon r. So we can from there make epsilon r the subject of the formula, where we're going to then have the absolute permittivity divided by the permittivity of free space in this case. Then we have the wavelength that I've explained earlier, that is C is equals to F lambda. Another formula for wavelength is 2 pi over beta, where our beta is what is the propagation. Now we can, from the question, some of the question asks us to find the instantaneous and then the average power density. When we want to consider the instantaneous power density, that is when we are looking at the, of course, the e raised to power g omega t is going to be introduced into our listing, into our calculation, and then the average power density, that's 1 over 2, the multiplication of these electric fields, E and H. So when H conjugates, rather, so half E times H conjugate, that is the average power density, and it is otherwise known as the Poynting vector. So we have the magnetic energy density. The magnetic energy density, as simple as it is of course the energy density that's considering 1 over 4 E. We know that half CV square, right? So you can then from there say that half times E square, that's an half multiplied by epsilon times E square. Yeah, that is the energy. Sorry for disruption. Now, and then it is measured in watts seconds per meter square. This is measured in watts per meter square. Now we are going to be considering the oblique incidence as well. And then oblique incidence is when the angle of propagation is at an angle, the angle of incidence. The incidence wave is moving at an angle, and then from there we are going to be considering our K1. In that case, since the wave is not moving in only one direction, it's moving from only one principal axis, then we are going to be considering the propagation constant at the first medium, and then the propagation constant at the second medium. At the same time, we are going to be considering the angle of incidence. Propagation constant at the first medium, that's just like the magnitude. When you take the square root of the 2 beta, and then you square them, then you're going to get the K1. From K2, you can in the second medium, it depends on the second medium of consideration. If it happens to be like copper, of course, it's going to be that's K1 over. We are going to use the effective wavelength. The effective wavelength is going to be mu naught over epsilon r. That is when a wave is moving from air to like copper. Where epsilon r is the relative permittivity of that of copper. The angle of incidence as well. The angle of incidence, that is of course you can see that is a tan theta over the magnitude of the vertical axis over the horizontal axis. You have the transmission. We know that the transmission, that is the addition of transmission from plus reflection is equals to 1. So when we subtract 1 from our reflective coefficient, we can get our transmission wave. We have the energy velocity, and energy velocity is always less than c. Is always less than the velocity of free space, which is 3 times 10 raised to power 8 meter per second. And then the phase velocity is always lower. I mean, this is always greater than our c. The next we are going to be looking at is the polarization. Now, in polarization, we are going to be considering the linear polarization, the circular polarization, and the elliptical polarization. A polarization is said to be linear if one of the magnitude is 0. That is, Ex can be equals to 0 where we have Ey, or Ey is going to be 0 where we have Ex. In that case, the difference between the two phases is going to be what? It's going to be infinity or is 0. So we say it is said to be linearly polarized. And then in linear polarization, we don't have left polarization or right polarization because what? Because there's no phase difference. The phase difference can be 0 or infinity. Now we have the circular polarization. Two waves are said to be circularly polarized if Ex, the magnitude of the wave in the x-axis, and then the magnitude of it in the y-axis is said to be the same. When they have the same magnitude, but the phase of 90-degree difference, then it is said to be circularly polarized. If the x-axis leads the, let's say, the y-axis or the z-axis by 90, it says to be the wave is going to move in clockwise direction. In that case, it says to be right and circular polarization. That's the sense of the rotation, right and circular. However, when the x-axis, which is known as our vertical axis, is lagging the phase of the second wave, then it's going to be in left polarization. Then the sense of rotation is going to be in the anti-clockwise direction. Going forward to the elliptical polarization. The wave is said to be elliptical polarization where, in circular polarization, they must have the same magnitude. However, in elliptical, they must not have the same magnitude. When the magnitude is not the same, however, there's a phase difference, definitely it's going to be elliptical polarization. Most of the times, usually 45 degrees, that's lambda by 4 phase difference. And then if the x-axis is leading by lambda by 4, definitely it's going to be what? Right hand elliptical polarization. However, if the left, if the z or the y-axis is leading by what? Is leading by lambda by 4, even by 90, lambda by 2. Here, it says to be left-handed elliptical polarization. So that is just a short summary of the chapter 4. We're now going to move forward to chapter 5, and then it's still the transmission and reflection of electromagnetic wave. And then we know that our reflection coefficient, that is equals to n2 minus n1 over n1 minus n2. That is, of course, the diffractive index in the first medium minus the diffractive index in the second medium over the addition of the two. That is our difference. And then the transmission coefficient is still the same, which is what? Which is the addition of, when you add 1 to our reflective coefficient, you're going to get the transmittive coefficient. From there, we can go to our Snell's law, our common law in physics, which is the Snell's law. And the Snell's law, of course, the sign of the angle of incidence, n sine theta. The theta is the angle of incidence, is equals to n2 sine theta. Then that's the reflection theta, that is the n, where n1 and n2 are the refractive indices of the first medium and that of the second medium. We have the boundary condition. The boundary condition states that the electric field, that the tangential component is continuous. It means the incidence wave plus the reflected wave is equals to 0. So that is while the normal component is the H is continuous in that case. So the question here asks us to find of course, the difference of the exciting power density and that of the incidence power density. We are going to make use of this formula to arrive at our final answer, which is when you take the transmission coefficient of when you are considering the first medium and the second medium, multiply by that of the first medium and the second medium, and then the reflective coefficient square. So that is that about that. Now going forward to our question. Oh, yeah. The first question, which is 4.8, it says the wave is going in minus z direction. What's going to be the magnitude of the beta? In that case, the magnitude of the beta is going to be positive from our stated formula for electric field. Now, in an unbalanced source free means the J is equals to what? J is equals to 0. It means just like a free space. Yeah. Assuming that Ex and its value is z equals to 0. This is the magnitude of Ex. The magnitude of Ex is 4 times 10 power is, and then the frequency is equals to 3 megahertz. The F is given, and then they ask us to find the complex electric and magnetic field. So we are going to write the complex electric field by E, which is the value that has been known, E raised to power minus J beta Z. However, this is going to be plus because it is moving in negative Z direction, right? Because it is moving in negative Z direction, it's going to be what? It's going to be plus beta. However, we don't know our beta. We have to calculate our beta from 2 pi over lambda. Yes, 2 pi over lambda, where lambda is the wavelength. How are we going to calculate our wavelength? We know that C is equals to F lambda, and then C is equals to 3 times 10 to the power 8 meter per second. And then our F has been given to be 300 megahertz. So we are going to divide 3 times 10 to the power 8 by this. Then we are going to align that at our lambda. From that, when we get our lambda, we're not going to use it to calculate the beta, which is going to be so it means this has been already been calculated. I'll definitely show you my calculation here so that you can follow it. Now, the second is when you want to calculate the magnetic field, the complex magnetic field. The complex means that you are going to put the exponential term into it. So the magnetic, that's Ke over the impedance, the wave impedance, Ke over eta naught. So eta naught is equal to 377, since it is in the free space. Is that okay? That's 120 pi. So yeah, and then it is in what? It is in ex direction. It means the unit vector is what? Is ax. Okay? It is in the unit vector for the E is ax. However, the unit vector for when we want to calculate our k is going to be in minus ax. When we say minus as cross a, I mean minus az cross ax rather, minus az cross ex. What's going to be the final answer? The final answer is going to be, when we say ax, when we say ax, of course it's going to be ay. However, because of the presence of the minus, we are going to have minus ay as the unit vector of our magnetic field. So that is that about that. You just multiply the two and you arrive at the h. Then don't forget the unit. The unit for magnetic field is ampere per meter. Now the instantaneous electric and magnetic fields. The instantaneous means you are going to introduce the e raised to power j omega t term into it, and then this is then going to contain the e raised to power j omega t terms. We are going to be having 4 times 10 raised to power minus 4 cos. We are going to introduce the cosine omega t minus beta z, and then the magnetic field too, we are going to change this to what? Change it to e raised to power j. You introduce the time derivative e raised to power j omega t into it. Then number C, that is the time average. Time average means 1 over 2. When you multiply the electric field by the conjugate of the magnetic. And what do we know as the conjugate? Conjugate of magnetic, that is when you change the complex, then you change the sign of the complex form. When you change the sign of the complex form, when it is minus before, you change it to plus. When it is plus before, you change it to minus. That is the J term. You are going to what? You are going to change the sign. Then when you cross product of the two and then you divide it by 2, you are going to arrive at our time average power density. And don't forget, the unit of time average power density is measured in what? Is measured in watts per meter square. The instantaneous power density, when you say instantaneous, as I explained earlier, it means it's going to contain the what? E raised to power j omega t terms. Of course, it's going to has a cosine term. So now going to number D, they ask us to find the average, time average, and instantaneous electric and magnetic energy density. Time average, magnetic energy density, that's 1 over 4 times what? Epsilon naught E square. This is synonymous to the energy in the capacitance of a capacitor, that is, which is half CV square. Of course, where the C is what? Where the C is like the, in this case, like the constituted parameter of epsilon naught, and then that of the C is like the E in this case, V is like E in this case. So we are going to be looking at the magnetic density, and then this in magnetic energy density, we are going to have mu h square, mu h square. So that's about that. Now I'm going to show you my calculation, how I arrive at everything. As I explained, it still follows the same procedure as I explained earlier. Now this is it. You can see the formula, this is the formula for our electric field, and then how I arrived at our beta, as I explained earlier. Then the formula for the magnetic field, which is K times E, where K is the unit vector of the what? That's it. K is the unit vector of the direction of propagation. In this case, since we are using Z, it's going to be A. Since we are using Z, it's going to be minus AZ. You understand? That's since the wave travels in negative Z direction. So when we multiply it, as I said earlier, it's going to be minus AY. So we're able to arrive at this. Our B asks us to find what? It asks us to find the instantaneous So that's what led to this. Our average energy, our average power density is this, which is, I said, A cross H conjugate. So that's how we're able to get this, and then we're able to arrive at this. The last one, which asks us to find the magnetic energy, 1/4. And I said this is similitude to half CV square, right? Half CV square, however, because we are considering energy, is going to be 1/4 epsilon naught E square. This is just like V, infinity square, and then epsilon naught is our constituted parameter is like C. Okay, so now that is that about that. That of the magnetic. These 2 days we are going to the constituted parameter in magnetic is mu naught. Okay, so now that is that about the number 4. So simple. Now we are going to our 410, which is 10. That is chapter 410 question. And then it asks us to, it gives us, okay, let's first explain everything about the question and then explain how it is solved before going to the questions, and I can cross-check how it was solved. Now, they gave us the electric field to be this, right? Z is the meter. They give us the F 100 megahertz. Mega means 10 to the power 6, right? They asked us to find the phase velocity, VP. The phase velocity, what was the phase velocity? The wave, where is it traveling? It is traveling in a ferrodielectric medium. Ferrodielectric, this is different from when it was traveling in free space in number 1. This is traveling what? In ferromagnetic medium. And then from here, we have been able to get our beta. This is our beta 2 pi. It means the wave is moving in positive direction because of this expression. And then we have been able to get our beta, which is equals to what? It equals to 2 pi. That's our beta. So from there, we can get our wavelength. Since we know that our wavelength is equals to what? It's equals to 2 pi over beta. Then 2 pi divided by 2 pi, that's 1 meter. That is for the C. Going to our epsilon, to the dielectric constant of the medium, that's epsilon r. Since we are considering E, that means it is H. If they ask us to find the dielectric constant, that's going to be what? That's going to be mu r. But in this case, because we are considering E, is going to be what? Epsilon r. Now, and then we already know that C is equals to what? VP. Of course, our VP is equals to C over what? C over square root of epsilon r. Okay, but our epsilon r is not given. That's why we want to calculate the epsilon r. How are we then going to arrive at epsilon r? That's the question begging for answers. And then we know that our mu. So we know that from our beta, we can be able to arrive at what? Our epsilon r. And then C is equals to what? F lambda. We can from there get our what? Get our phase velocity. Then we can get our dielectric constant, epsilon r. Then the time average power density. Time average power density of S cross. That's the cross product of what? The cross product of the electric and then magnetic. The magnetic field is not given. You have to calculate our magnetic field by using our normal formula or using the familiarized down through. We can use our formula that Ke over what? Over lambda, no, over wave impedance. Over wave impedance. In this case, not 377, because what? Because it is moving in unbounded non-ferromagnetic direction. That's 377 over epsilon r. So then we are going to use the 377 over epsilon r to get the n in this case, or eta rather in this case. So it's going to be K times E over eta. So that is that about that. Because of that, we are going to find the conjugate of it, and we're going to multiply it by cross product it by our E to get the time average. Don't forget to divide it by 2. Then we have the time average total energy density. That's 1/4 epsilon naught, right? E square. Epsilon naught E square. That's for the electric field. We are going to calculate that of the magnetic field too. That was going to be what? 1/4 mu naught H square. So then you are going to do what? The total. You are going to sum the two. You are going to add the two. So that is all about question 4.10. Now you can check the question, how I solved it here to know to follow the same procedure. Now this question, I said we were given ay to be 10 raised to the power minus 3 raised by this. Then we were given the f, right? At the same time, the beta, I explained the formula for calculating the beta, and then it's omega over beta. Omega is equals to 2 pi f from our elementary physics. Then f is given, our beta has been known from the given electric field 2 pi. Then we divided it to arrive at this 1 times 10 raised to the power 8 meter per second. Is this less than the frequency of free space, the velocity of free space, or it is greater? Less than it, yes. So the beta is going to be epsilon naught, I said, and then C is also exactly as is explained earlier. Same thing is applicable to the lambda, which is what? 2 pi over 2 pi, which 2 pi is 2 pi from the formula, 2 pi from beta. So that was how we were able to arrive at this. That is that about the wavelength, and then that's that about the time average power density. That's that about the two. The same thing is applicable to this as well. I explained earlier where we are going to arrive at 1/4 epsilon naught joule per meter square. Don't forget the units. It's the same as watt seconds per meter square, since we know that power times time, right? That's equals to energy. And then the total, you calculate the energy of the electric field and then the energy of the magnetic field. You add the two together. That's going to give us the total time average energy density in the medium. Moving forward to the next question. If there is any question, you can actually send an email to me. Now 4.15, which is if they give us the electric field to be this, right? From this, which type of propagation is this? We can be able to understand from this that it is what? This is not a normal incidence, but what? But an oblique incidence, because the wave travels in what? In y direction, and at the same time in what? In z direction. So assume that our distances determine the angle of wave travel. How are you going to determine relative to the z axis? This is that of the c axis. You're going to determine the what? The angle. The angle is going to be what? Cos theta times what? 8. Okay, 0.8 rather, because you are going to c square plus 8 square root, that's going to be 10. And then our propagation in z axis is going to be what? 8 over 10, which was 0.8. So when you take the cosine of it, then you are going to add 0.00 something, 0.3 something. That's going to be the angle of wave travel. Any question from here? In z direction, in z axis. Note that. Now we are going to, from there, we are still going to, enemy, we want to use the y, that's going to be the sine. So when you take the arc sine of the 0.6, you are going to arrive at the same answer, which is 0.6, 0.3 something as our what? As our theta. Don't forget that it is in degree, right? Not in radian. Also, the three-phase constant of wave along it. There's no diagram. I should have shown you a diagram to explain this. However, the three-phase constants of the wave along it. So the phase constants, we have the first K1, which is what? When you take c square plus 8 square roots, that's going to be 10. That of the y 6, that's the phase constant. The phase constant you're talking about is the beta, and don't forget in rad per what? In rad per meter. That of the last one, z direction, is what? Is 8 rad per meter squared. Those are the three phase constants in its oblique direction. That of the oblique direction is 10. That of the y-axis is what? Is 6. That of the z-axis is what? Is 8. Now, going forward to the three wavelengths of the wave along it. The wavelength, we know that wavelength is equals to what? 2 pi over beta, then 2 pi over beta 1, that of the oblique incidence over what? 2 pi over 10. That of the oblique incidence, that of the y-axis is going to be what? 2 pi over what? Over 6. Out of the Z, that is going to be 2 pi over 8. As simple as that. The number D is asked us to find the three-phase velocity of the wave along the oblique incident. The phase velocity. Note, are you forgotten? Among the two, which one is going to be greater than which one is going to be greater than C, which is the 3 times 10 to the power 8? That's the velocity of free space. Which one is going to be lower? So we know that this is going to be what? It's going to be greater, while the energy is going to be lower. So from here, you can be able to understand that the first one is 10 times C over what? The first one, which is in the oblique incident, is going to be what? 2 pi over the phase velocity, omega over beta, right? Omega over beta. Omega is equal to 2 pi F over beta. The beta here is going to be 10. So it means you are going to what? Multiply it by C. When you multiply this by 0. When you multiply it by 10, it's going to give us the final answer. When we multiply it by 0.6, that's 10 C, 10 times 6 divided by, no, 10C. It means 10 times 3 times 10 by 8 divided by 6. That's because when you divide 0.6 by 3 times 10 by 8, that's going to be what? That's why it's going to be what? Greater than our C. The same thing is applicable to this 10 times 8 divided by 10. So, and in this energy velocity, you are going to interchange the answer. You are going to interchange the from 10 to 8. No, it was already 10 over 8 before. It's not going to be 8 over 10. And then what? C is over 10. That is that about that. And then that in the area of the oblique instead, because it is moving in the free space, definitely it's going to be what? It's moving from free space to another. That's going to be 3 times 10 raised to power 8 meter per second. Now the frequency, which is F, we've known our what? Omega is equal to 2 pi F, right? From there, we can be able to get our F. From there, we can be able to get our what? We can be able to get our F. Associated magnetic field. This is very, very important because it is different from the ones we've been doing before, because when we want to use our formula that K E over theta, we want to use the formula, it's going to be what? The K in this case is not just going to be only AY alone or only AZ alone. It's going to be AY and AZ, and you're going to consider the numerator, the arguments, these arguments. When you take out the 10, which says like the beta, definitely this is going to remain 0.6, and then you have to change it in such a way that it is going in positive direction. Then it is going to be minus 10. This is going to be minus 10. When it is minus 10, it's going to be minus 0.6 AY, and this place is going to be what? Plus 0.8 AZ. That's our unit vectors. Then you are going to multiply this our unit vector by what? By this value. You're going to arrive at minus 5. And then when you multiply this by this, you multiply this by, you do the cross multiplication of all, you're going to arrive at our answer. That was how I was able to arrive at it. From this place, I'll be able to show you question 4.15 now. Question 4.15, this is it. The K1, the first K, is 6 square over 8, right? When you take the square root of it, as I said, it's 10. And then when you do what? Okay, this is the E given. These are cosine. So you should calculate it in Z axis. Because we are calculating it in Z axis, that's why we made use of what? That's why we made use of 0.8. That's 36 times this. Not 0.6 as I made a mistake earlier. That's 36.86999. If you are considering it in Y axis, of course, that's going to be 0.6. When you take the arc sign of 0.6, you are going to arrive at the same answer. Now, moving forward to the three-phase constant of the wave. The phase constants, these are the wave constant, the 10, 8, and 6, right? Next is the wavelength. This is the wavelength, 2 pi over what? Over K. K can be used as beta interchangeably, depending on the condition. So the first K, that's in the oblique incident, that is 10, right? This 10. So when it is 10, of course, that is we are now going to arrive at 0.6 to 8 meter. In this case too, when our 2 pi over The K here, that's that of the y-axis. This here, that's that of the what? That's that of the z-axis. The next one is our phase velocity. Our phase velocity for the free space, that is the 3 times 10 to the power 8. That is the oblique this thing. That's the oblique incidence, 3 times 10 to the power 8. However, for the y-axis, you're then going to 10 times c over 6, where c is the what? 3 times 10 to the power 8 meter per second. That's the velocity of free space. Now, the times 10 to the power 6, that's you are going to arrive at this. This, as I said earlier, our phase velocity is going to be greater than the velocity of free space. The only thing, the only difference between the phase velocity and the velocity is that in that of the energy here, you are going to interchange 10 by 8 and 8 by 10. So in that case, the energy velocity of the wave along the oblique incidence, along the y-axis, along the z-axis, they're going to be what? It's going to be less than that of the oblique incidence. As simple as that. Now, that exactly what was done here. What was done here. There's that cos theta that is going forward to the cos theta 0.8. That is 10 divided by 8, right? Yeah. Rather, that is 8 divided by 10. I said we will interchange 10 to say in phase velocity and the energy velocity. Now, the next one is f, which is the frequency. I said omega is equals to what? 2 pi f. And then when you make f the formula, I'm going to calculate our omega, and then the c is equals to what? Omega over beta. Then from there we can be able to calculate our omega, since we know now beta to be 10, right? 10 times 3 times 10 to the power 8. Then you're going to get our f. There we were able to arrive at the answer for f. That happens to be 4.7 times 10 to the power 8. And hertz, don't forget the unit of frequency is measured in hertz. Now the next one is associated magnetic, that's H, the associated magnetic field. As I explained earlier, that you are going to consider the argument of the argument of the direction of propagation minus 0.6 AY. All this has been explained because it's just like moving in. I put this here so that you can easily remember. It's just like moving in what? Minus 10 direction. Okay? It's just like moving in minus 10 direction. Then you're going to consider the minus, you're going to interchange the sign. So when you take the cross product of the unit vector, you're going to arrive at what? I said minus 5 the other time. I must say it. Yeah, this is it. So from there, you will be able to get your what? You will be able to get your magnetic field. Moving forward to the next question, which is let's do it the same way we've been doing it from the beginning. That is a 4.1. Sorry, that is a magnetic field intensity of plane wave in a lossy earth. The lossy earth, definitely it's not in free space in this case. We are going to consider the lossy earth. Okay, it means it is lossy, not in free space, that is lossless. Then they give us our H, which is the magnetic field. They give us this formula. Okay, it flows in what? In which direction does it flow like this? And it means it flows in positive x-axis. Okay, it flows in positive x-axis. However, because it is a lossy, we are going to consider the attenuation constant and then the propagation constant, which is with the summation of the two leads to gamma. So now this is the magnitude of magnetic field, and then that of them. They gave us the conductivity, which is rho, to be this. Just why did they give us the conductivity? So that we can be able to test our what? Our medium. Is it a dielectric, a good dielectric material, or is it a conductor, a perfect conductor? How do we know that? There is a formula that when we put it there, if it is greater than 1, then it is a conductor. However, if it is less than 1, it is what? It's a dielectric material. Then we are going to use the right formula to get the what? To get our beta and then the alpha as well, so that when we are getting the electric field, we are going to substitute the formula into it, and then that will be necessary while calculating our screen depth, which is a meter. That's like the distance. That's the inverse of the attenuation constant. So from there, we can be able to get our attenuation constant. So the formula for the attenuation constant when it is what? When it is a either perfect dielectric material or it is a perfect conductor in NEPA per meter. When they ask us to find it in linear scale, no, when they ask us to find it in decibel, we are just going to take the 10 log of the answer, then you're going to get the answer in decibel. The wavelength does not change, that's 2 pi over beta. However, the beta we are going to be considering here is going to be what? The beta in the lossy media, and then the that of the lossy media, that's what? Okay, the phase constant as well, which is the radial part, that's the phase constant, that is the alpha and the beta. So, and they ask us at the same time, they ask us to find the power density. That's when you take the average of the product of H, no, the product of E, right? Cross the conjugate of H. You're going to take the conjugate of, when you want to take the conjugate of H, how are you going to go about it? You're going to change this to minus. This says it contains the J term. Okay. This is going to be left the same because it does not contain the complex J term. This way, you are going to change this to what? You are going to change this to plus because it contains what? It contains the J term. That's just the conjugate for you. That's the trick. So that's the easiest trick of getting the conjugate of a vector. So that is just how. So the procedure is that you test the conductivity first by using the specific given formula. When it is greater than 1, it is a conductor. When it is less than 1, it is a what? When it is less than 1, it's a perfect dielectric material, that is an insulator. So that will now give us the actual formula to use. However, the formula is not yet useful because while calculating the corresponding electric field, what will happen? You're just going to use your formula that what? Instead of KE, right? Instead of using KE over what? Over the wave constant, that is used for getting the H. When we want to get our E, we are going to multiply the wave constant by the what? By the H after getting the K. However, when it is negative, when it is going in positive direction, you are going to use minus what? Minus H. However, when it is going in positive direction, you are going to use plus H. However, this is going in what? This is going in positive direction, then you are going to consider minus H. Minus KH multiplied by the what? Multiplied by the impedance. So that is that about that. Now, you can understand the explanation. Let's now go to my soft example, soft work, so that you can be able to follow the right formula. 2.1. This is the this is a 2.1 as can you see minus nk. This is the unit vector as I explained to you earlier, and then what's going to be that's going to be what? Ax, because it's going in positive x direction. Okay, now your unit vector is going to be what? It's going to be AX in this case. However, the first step is that you test the conductivity. This is the formula for testing the conductivity of material. When you test rho over omega epsilon, that's just the constituted by the constituted parameters. When you divide the rho by omega and then epsilon, you are going to arrive at that. And then how are they able to get our omega? Omega is equal to 2 pi f, right? And then f is given 2 pi times this. That was why we were able to arrive at our omega. And then the epsilon is epsilon naught, epsilon r. Epsilon naught is 8.8 times 10 power minus 12. That's 1 over 36 pi times 10 power minus 9. So when you multiply it by the epsilon r, which is 9, then you're going to get the that is the absolute permittivity, right? So when you multiply it by the epsilon r, which is relative permittivity, you're going to arrive at this is the permittivity of free space. This is the relative permittivity. When you multiply it to that's absolute permittivity. When you now test this formula, if it is greater than 1, it's going to be what? It's going to be a conductor. However, this is less than 1. It means it's a dielectric, perfect dielectric. This is an insulator. So you are going to go to the formula for calculating that of the insulator in order to get our what? Wave impedance. This is different from that of the conductor. So use this formula because it is a perfect electric. So now our H has been given. Then from there we can be able to get our E, which is what? This. And then take note that the AX has the K. We are using this formula now. This formula we are using for this. This formula we are using for this. Okay, our K is what? Is AX because the wave moves in what? In X direction, right? So when you multiply AX by AY, is going to be what? Is going to be AZ positive. When you multiply AX by AZ, is going to be what? Minus AY. Okay, this is J, they replace this. And then don't forget that this J is going to what's going to change. No, it's going to remain the same. However, that of the H is going to change when we want to calculate our what? Our what's it called? When we want to calculate our average power density. Yes, we want to calculate our average power density because it's going to be equals to half multiplied by E multiplied by H conjugate. So while calculating the conjugate, we are going to change the sign of what? Of the J term, of the exponential term. So this is the formula. We can use that formula, or at the same time, we can make use of this same formula. And we know that from our elementary physics that our what? R is equals to V squared over R. Okay, this is just like V, which is E. This is just like the resistance. This is the wave impedance. Okay, so it follows. So we're going to use the same thing we did here to arrive at our final answer. And then this is what? This is watts per meter square, not cube. This is an error per meter square here. This is watts per meter square, right? So that's about that. The next one is phase velocity. The phase velocity, go and look the formula for that of the dielectric. Don't use that of the conductor, or don't use the normal one. So that's 1 over mu epsilon. What mu naught mu r. Okay. However, in this magnetic material, mu r is equals to 1. Okay. Epsilon r is equals to 9. Don't forget the permittivity of free space, that's a constant. Don't forget the mu naught, that's permeability of free space, that's 4 pi times 10 power minus 7. Yeah, Henry per meter. So you substitute all into this to arrive at our phase velocity. So that is that about that. The next one is calculating the beta, which is the propagation constant. Use the same formula, calculating our E, that's 2 pi over beta, the same beta we got here. Why is it? That's the effective wavelength. This is different from mu naught, which is that of free space, which is what? From we can be got from V is equals to F lambda, where V is equals to 3 times 10 to the power 8 meter per second divided by frequency. This is different. However, you can arrive at it by doing what? Dividing dividing the wavelength of free space divided by what? Epsilon r. Okay, we have epsilon r, the square root of epsilon rather. So we are going to arrive at the same answer. Then the attenuation constant, this is the formula for attenuation constant when we are considering the dielectric material or insulator. So it's measured in Nepal per meter. When we want to change it to a logarithmic mode, that's in decibel, we are going to multiply it by what? We are going to multiply it by, we are going to take the 10 log of it. Okay. Also, we are asked to get the skin depth. I said earlier, the skin depth is just the inverse of the reciprocal of the attenuation constant. So when you take the reciprocal of the attenuation constant, it's going to be meter. So why is it not meter per NEPA? Why is it that it's only meter? Just because NEPA is they are just like radian, they're just existing in our calculation just to differentiate it from normal per meter. Sometimes attenuation constant can even be written as per meter. Okay, so that's why it is a meter. It has no effective. The next one we are going to be looking at 4.25. We are going to be looking at 4.25. That is they give us h to be 10 raised to the minus 3. They ask us to they give us the magnetic field. They ask us to find the polarization of the wave, which take the time. SubhanAllah, our time has been fast spent. They gave us the propagation of the, they asked us to find the polarization of the wave. Merely looking at this wave, how do we get the polarization? By the first step is that you are going to look at the magnitude of AX, the magnitude of AZ. Are they the same or different? If they are the same, two things might happen. If they are the same, it means it's circular. And can we use that to conclude that it is circular? It depends on the yes or no. No, it depends on what? It depends on the the phase difference. So if the phase difference is 90-degree, definitely we are going to conclude that it is circular. However, if the wave difference is infinity, it means what? No polarization at all. Okay. Can we say it is linear? You can only say it is linear if one of the magnitude is 0. That is, there's no magnitude of 1. So in this case, minus j means it is what? It is minus 90 degree. It's ax has the magnitude of minus 90 degree. This has that of what? That of a 0. It means ax is leading az by solar. It, ax is leading ax is leading ax is leading az by 90 degree. In that case, is it right-handed polarization or left-hand side? Because AS is leading, it means it is going in this direction, it means it is going in clockwise direction. Because it is going in clockwise direction, it means it is right-hand circular polarization. So the answer is circular polarization, and then the direction of rotation, that is in clockwise direction. Okay, because AX is leading AY by 90 degree, it means the AX is lagging behind AZ is lagging behind AX by what? By 90-degree phase. So it means it is a clockwise, it is circular, right-handed polarization. This is also sketch the polarization curve I'm going to show you in this. That's 4.25. 4.25, see, circular polarized. It is circular and then it is right-handed. It is clockwise because what? X leads Z. Because X leads Z. They ask us to get the what? To sketch the curve, and then you cannot sketch the curve without getting the h. Of course, you get the magnitude of h, that is hx plus hy. When you take the square root, that is the magnitude of this and this. When you take the square root of it, you are going to arrive at this answer. You get the phase difference. The phase difference is what? One is 90 degree and one is what? One is 90 degree hs of that. So tan omega t. When you take the acta multiplied by tan, you're going to cut the 2. Then you are going to arrive at omega t only. Then you can from there draw our curve. This is our curve. As can be seen, this is our curve. Now moving forward to the next question, which is 4.31. Let's do it the same way so that it will be very fast. We just explain the procedure, and from there we can be able to go back to the question. Okay, 4.31, they gave us E, of course, to be this value. Beta E are a constant, already know. Assume E plus J omega T time convention. Assume E plus J omega T time convention. The polarization of the wave. How do we get the polarization? Merely by just looking at this. Merely by just looking at this, how do we get the polarization? In order to get the polarization, the first, just as we did the other time, we look if they have the same magnitude. AX, what's the magnitude of X? What's the magnitude of Y? Are they the same or different? If they are the same, then we will be looking at the circular. However, in this case, they are different. Because of the difference, then it is elliptical. And can we conclude from there that it is elliptical? It depends on what? The phase difference. The phase difference, G is leading, AX is leading by what? By 90 degree. And it is 0 degree. Since AX is leading by 90 degree, it means it is elliptical. It is elliptical polarization. And is it right-handed or left-handed? AX is leading. Because AX is leading, it means it is right-handed. And because it is right-handed, it is going in clockwise direction. So that's the sense of the rotation. The sense of the rotation is that it is going in what? In clockwise direction. So it is this elliptical going in what? Clockwise direction. The Asia ratio, that's just the difference between the magnitude of the AX and then that of the AY. That of the AX and that of the that's the fast over what? Over horizontal. So negative, and from there you can be able to get our Asia ratio, which is AR. So this is what has been done here for 0.13. 0.13, everything has been done here. This is X. It is going in clockwise direction because what? Because X is leading Y by 90 degrees. The magnitude of what? Magnitude of A divided by the magnitude of AX. You're going to arrive at this answer. Then this is the diagram. This is our curve. Even though it's not asked, they did not ask us to calculate the curve. However, it is shown just to explain that it is elliptical and then it is going what? In clockwise direction. And then that's why it is a right-handed elliptical polarization. Now, going forward to the next question, that is question 5.10. But now we have spent around an hour going to now 5.10. They gave us a diagram and they asked us to find the what? Reflection and transmission coefficient. What was the reflection coefficient? I've told you the formula for calculating the reflection coefficient, and then the transmission coefficient is just by adding 1 to it. Then from the diagram, the slab is incidented normally in a lossless slab. This is the thickness. This is the thickness. This is the first medium. This is the first medium rather. This is the second medium. This is the third medium. This is in free space, which is air. That's why epsilon naught mu naught. This is in air. However, this is the slab, which has the epsilon r is what? It has an epsilon r of separate this thing, not one, no, not 1/36 pi times 10 to the power minus 9. Okay, that's that of mu field squared. That goes to epsilon r. Epsilon 1 is equals to what? Epsilon naught, epsilon r. Okay, from here you are going to add the incident wave and then the transmission wave. That's the what? That's the reflection in the first medium. And then you are going to apply the boundary condition. What's the boundary condition? The boundary condition is that the tangential component of electric field is continuous along the what? Along the axis. However, the normal component of H is continuous, even though yes, H is continuous. We are going to add this incident wave and then the reflected wave, add the two together. Then we are going to calculate the H as well from our formula that KE over what? Over mu. So from there you can do what? You can substitute this into there in order to get that of. From there you can be able to get that of this place too. And then don't forget to leave your answer in terms of what? Media constituted parameter. What are the media constituted parameter? That's mu, epsilon, and what? Rho, mu, epsilon. And then the thickness, it is T. So that is done. I'm going to show you the derivation from here without wasting much of our time. This is the derivation. The first medium, second medium, right? The first medium, which is this place, which is a free space. Third medium is in free space, which this is the what? This is the medium, which is not free space. Okay, that's the step. So I said we are going to add that of the incidence and then the reflection. When you add the two, for E2, incidence plus what? You can see from here that incidence, this is the incidence, this is the reflection. And then from 3, you can only see what? You can only see the incidence. The what? The reflection is not there. So you are going to put only the what? Only the incidence there. The reflection is not there. Then from there, you can apply the boundary condition x equals to 0. That's equals to the tangential component of is continuous, means E incidence, and then E reflected is equals to E2 incident across this interface. Across this boundary, we're going to we've applied the boundary condition there. Then our H is equals to E1 minus mu naught. That is mu naught in the first, that's 377, right? 120 pi. Okay. However, that of the second medium, that is E2 minus E2 incidence and then E2 reflection divided by what? Divided by our N. And then our N in this case, what? N naught over epsilon R. If we are given epsilon R, we can be able to get our N1. That's the wave impedance 1. And from then, when we substitute these into this, we are going to arrive at the answer for the what? For the calculation of the expression or the total reflection. And we are now going to the total. These are just the incidence E1 and then the reflected E1. That is the reflected wave at the face, at the stab. Okay. Moving forward, we are going to apply the boundary condition at this as well. It means the electric component across this, and then they are continuous. It means they are the same. This is called E2 e raised by j plus this is equals to what? Is equals to that of E3. Yeah. And then there is the magnetic field over mu1. That's for mu1 over mu0. Why is it mu0? Because this place is free space. Of course, 377, right? 120 pi. However, this one is equals to divided by m mu0 divided by square root of epsilon r. If you know the epsilon of the, if you know the relative permittivity of the stab, you can be able to arrive at that. Now, solving the two equations, we can be able to arrive at the expression for the electric field in the second medium. The difference between the two media is that now you apply the boundary condition between the two, and then the electric field across the tangential component of it is continuous, right? Of course, the normal component of H is continuous. However, we apply that of electric component here. That's how we're able to arrive at all these answers. The next one is to express E3 and total transmission. How do you express E3 and total transmission? You already know the E3 to be equals to what? E2 over transmission. This is the formula for transmission wave. Not. How was it derived? You know that our reflection coefficient is equals to what? N2 minus N1 over N1 plus N2. When you add 1 to it, you're going to arrive at this answer. Then from there, you can be able to get the E3 positive and then E1 positive. What's that? That is the incidence at the stab divided by the incidence at this place. This arrive at the final answer here. And then don't forget our R, the same thing I told you the other time, N1 minus N0 over N1 plus N0. That's the what? Reflection coefficient. Then that of the total is equals to what? When you take the R over this, and then the transmission is this. So that's how we arrive at the derivation of them. And then don't forget that I left all my answers in terms of the constituted parameter. I did not change I did not put 377 as our mu naught. I did not put 1 over the t pi times 10 to the power minus 9 as our epsilon naught. I did not put 4 pi times 10 to the power minus 7 as our mu naught, right? So that's what the question asks us to find. Going forward to the next question, that is 5.2. What is 5.2 telling us to do? Okay, let's first explain the whole concept so that when we go back, you'll be able to understand better. It tells us that a linearly polarized wave, let's assume that the dielectric is present, then it gives us the epsilon r to be 2.25. Okay. Then that's also to find the ratio of the what? Excited average power density. Excited average power density to that of the incident wave. There is a formula for that. That's a very great shortcut. And then that is the multiplication of what? The multiplication of the transmission across the prism. Okay. And then that of the free space, when you multiply the two, and then you multiply it by the what? By the square root of the reflection, then you are going to arrive at the answer for the what? For the ratio of the two. As simple as that. Very straightforward. Now, you first consider this place when the wave is moving from free space. Okay. In this case, epsilon r is equals to 1, right? You apply Snell's law here. Okay. N times y is equals to this. When it gets to this place, okay, we calculate the critical angle. When we calculate the critical angle, is it going to be greater than 45 degrees or is it going to be less than 45 degrees? If it is greater than 45 degrees, what's going to happen? If it is greater than 45 degrees, it means there will be reflection, right? However, if it is less than 45 degrees, it means it is within the acceptance angle. Because it is within the acceptance angle, total internal reflection is going to occur. When total internal reflection occurs, what will happen? It means our what's total internal reflection? It means our R will be equals to 1. Our reflection coefficient is equals to 1 in that case. So, and then the angle at which this occurs is known as the critical angle. In the other way around, when we change the constituted parameter, we will known as the Bristol angle. The Bristol angle is where the reflection is equals to 0. This always occurs in parallel polarization. So let's now go what they ask us. Okay, yeah, I've explained what they ask us to find. That's just the when you multiply the transmission coefficients of the first medium, that's 0 to this, and then that of this to this, then you are going to arrive at that. Then you calculate the reflection coefficient when we are moving from here to here, from here to here. When you square the two, then multiply the three together, you are going to arrive at the difference between this. And what's going to be the unit to separate power density to the incidence power density? That's going to be this. What is going to be 1 because what meter watts per meter square will have cancelled. Watt per meter square 4.12. Let me show you how I arrived at the final answer here 4.12. That is this it as simple as the epsilon r is this. See the reflection coefficient 1 minus 1 for this place, that is our n is equals to what 4. No, okay, 4.12. Yeah, this is it. Our epsilon r is given to be 2.25. It means our n2, which is n across this place, that's the reflective index across this place, is equals to square root of epsilon r, right? We can, when we want to apply our Snell's law, this means our n1 is equals to 1. In here, the refractive the refractive index is 1. However, in prism, that's equals to when you take the square root of 2.5, that is square root of epsilon r, that's going to be give us the refractive. So when you take the difference between the two refractive indices and then you divided by the sum of the two reflective indices, we are going to arrive at our reflection coefficients. That's how we're able to arrive. So when you multiply this 2.2 square, okay, you keep it somewhere. You take the transmission to, and then what is transmission? Transmission is as simple as ABC. That is transmission. When transmission occurs, of course, you consider the angle of incidence at that case. That's when we were able to calculate the critical angle here. Because we calculate the critical angle was calculated to be what 4.81, which was lower than the 45-degree angle at the hypotenuse. Because of this, it means the incidence angle is within what? Is within the angle of acceptance. And this is the concept of fiber optics. When the incidence angle is what is lower than the critical angle, of course the light is going to be what? The light is going to remain in the core, not going to transfer into the cladding. Okay, so that's the principle behind fiber optics operation. Now going to so we got that scientists goes to this. So we're able to get this. Then total internal reflection is going to occur because what? Because our incidence wave is within the acceptance angle, the cone of acceptance, which is 45 degree in this case. So then our total internal reflection is going to occur. Our R is now going to be 1. So because our R is goes to 1, it goes to what? Our R12, that is when you are considering the second medium, this medium, which is 1.5, which was got from the square root of 2.5 minus 1 over this, then we're able to get 3.2. I said we are going to square it, keep it somewhere. Then transmission that goes to 1 minus what? Minus this. This is very reflection. When you minus 1 from the reflection, we are going to get our transmission. Okay? But this is the total transmission across the prism. Then R square, because we are considering the first when it is around this place and when it is in free space and when it is in the prism. So that we were able to get 0.95. The formula I told you before starting the explanation, that when you multiply the transmission across this 0 to 2, and then you multiply the transmission across what? Across 2 to 0, and then 0 to 2, and then you multiply it by the reflection coefficient square, then you are going to arrive at our what? You're going to arrive at the difference between the two. And will it have any unit? No, because what? Watt per meter square would have cancelled watt per meter square. So you can change it to percentage by multiplying by 100. So that is that about that. Moving forward to the next question, which is 4.15. That is telling us about We need to be very fast now because of the space. This is telling us the incident angle is 30 degree. Okay, epsilon equals to 4. That's this epsilon r. This the mu naught. Okay, this is the thickness. Decide also to find the angle theta 2. Theta 2. This is the theta 2. They also to find that's the. This is very simple. How are we going to go about it? You just apply Snell's law. N1 sine theta is equals to what? N2 sine theta. What's N1 here? N1 in free space, which is the refractive indices, which is the refractive index in free space, that is equals to 1. What is N2? N2 is equals to just taking the square root of epsilon r. So then sine 30. Sine 30, okay, is equals to what? Is equals to when you take the square root of 4, that is 2 sine theta 2. You can from there make theta 2 the subject of the formula, and then you are going to arrive at our theta 2 that was asked to calculate in degree. Then this is going to become what? It is going to become our incident angle at this place. This has become our incident angle. The angle of incidence theta 2. We're going to apply Snell's law at this place too. N2 sine theta 2 is equals to what? N3 sine theta 3. And what is N3? Because this is free space, is going to be 1. And what is theta 2? I mean, what is N2? N2 is just going to be square root of 4, which is 2. So from there, you can make theta 3 the subject of the formula. When you make theta 3 the subject of the relation, you're going to arrive at the final answer. That is that in degree, as simple, as straightforward as that. Let me show you how I arrive at it. This is a 4.13. 5.13 is it. Snell's law, you apply Snell's law, so you make what? You make theta 1 the subject, you make theta 2 the subject of the formula, you arrive at theta as this. The same thing with this. Simple as that. The next question is telling us about, the next question was got from Hulabi book. All the questions we've solved so far from chapter 4 and chapter 5, they were all taken from Advanced Electromagnetic book of Belanis. That is the second edition. The book I showed you at the beginning of this problem. However, this question was taken from the fundamental. The next questions we are going to be solving now, they were taken from the fundamental of electromagnetic wave by Dr. Hulabi. Now, this is a question what? It's question 8.3. That's like just example 8.3 in Hulabi book. So, and then it tells the question 10 of our problem here. They give us the frequency, and then this expolarized wave, it's going in positive direction from air to copper. Okay, from air to copper. What will happen? Because going from less dense to denser medium, right? Don't forget that at the Bristol angle, the of course the refractive index must be going from what? From a denser medium. N2 must be greater than N1 for us to arrive at R equals to 0. Okay. And then the angle at which this occurs is known as Bristol angle. When N1 is greater than N2, that is the device going from less dense medium to denser medium, the wave is going to reflect along the normal. When it reflects along the normal, there won't be reflection at all. However, when N2 is greater than N1, the wave is going to bend against the normal. Okay, the first one is bend towards the normal. The second one is going to bend against the normal. When it bends against the normal, total internal reflection can occur when the angle of incidence is greater or equals to the critical angle. So that's also the concept behind it. Give us so there's also to get the what, to obtain instantaneous electric and magnetic field. Instantaneous electric field, you already know our electric field in what? In air, that's in free space. Okay, it means what? When the several screen depth, this is another condition. I assume metal to be several screen depth deep. When it means it's short circuited, it means our R will be equal to -1. In this case, the reflection coefficient is going to be what? It's going to be -1 in this case. Now we can get our E. Let's go to the questions so that we can, let's go to the solutions so that we can quickly walk through it as we spend more than an hour explaining this. 10. Question 10. This question 10. Of course, in here, this is epsilon r and the incidence angle. This is the formula for it. This is for that of reflected. You see the minus because it is going in. Don't forget that it is going in the positive z direction. Because it is going in positive z direction, that's where the incidence is like this minus beta z. When it is reflecting back, it will be going in what? In minus z direction. And because it is going in minus z direction, it's going to be what? Plus beta z. Okay, so from there we can, of course, from the this thing, they ask us to find the instantaneous electric field. And when you say instantaneous, it means what you are going to introduce the omega t term. In this case, when we introduce the omega t terms, that's going to contain the cosine omega t minus beta z, and only beta and omega is not known in this case. We calculate our beta. Our beta is equal to 2 pi over what? 2 pi over k naught. Our beta is equal to 2 pi over mu naught, and mu is equal to what? Mu is has already been known to be what? Mu is equals to v is equals to f lambda. I mean rather lambda 2 pi over lambda c is equals to f lambda. We are going to multiply 3 times 10 to the power 8 meter per second divided by our f that has been given to be what? Divided by our f, we are going to arrive at our, that's where we're going to get our mu naught. From our mu naught, we are going to get this. Because this is given, we are going to test the conductivity of the material. Is it greater than 1 or less than 1? If it is less than 1, it's a dielectric. That's an insulator. However, it is greater than 1, it is a what? It's a conductor. So we are going to make use of the formula of the conductor if it's greater than 1. However, if it is less than 1, we're going to make use of the formula of insulator. In this case, it is greater than 1. When we check the constituted parameter, so this is 10 times 7 power 9. It is a metal. It means it's a conductor. Then we are going to make use of the formula. It means our mu is going to be what? This mu, why is it needed? Because when we want to calculate our h, ke over eta rather, eta. So it means when we want to calculate our h, it means we have to do what? We have to divide it by what? By eta. So this is the formula for that of the this is the formula for that of a meter. You see the formula? Here, when you press the calculator and you get the magnitude is 11. Then you calculate the reflection coefficient. When you calculate our reflection coefficient, then 2 minus n to 1. So our is going to be minus 1, as I told you the other time, that it's a short circuit because because of this statement, several spin depths. You don't even need to calculate our reflection coefficient because to minus 1. When we calculate this, it goes to minus 0.9999, which is approximately equals to what? Equals to 1. So we calculate this, the incidence electric field, which is equals to, of course, when you take this, that of the incidence, and then the reflection, when you add to do together, how were we able to arrive at this sign? We've been using this as cosine from the beginning. How were we able to arrive at this cosine? By using our Euler identity. Euler identity is that when e raised to power minus j minus e raised to power plus j divided by j2, then it's going to be sine. That j2 is what we put here just to complete it as I came on. Now, how do we get our h? Our h is simple. How do we get it? That's by multiplying k by e and then dividing it by wavelength, by dividing it by eta, which is our what? Which is our wave impedance. So that is what we did to get this. And so to get this, the last one is just expressing it in instantaneous form. Then we are able to arrive at this answer, which is 224 sine this. Then the last one is getting our what? I said ke over what? Over eta. Then we're able to arrive at this 64 times 10 square. And don't forget the unit. Unit is what? Unit is in mu ampere per meter. This is already what? This is millimeter. This is millimeter volts per meter. Okay, volts per millimeter rather, because this is our given magnitude is in millivolts per meter. Millivolts per meter. Now moving forward to the last question, which is looks like a complex question. It's just an oblique incidence, very simple. That's ABC. Let's quickly dive into the explanation of the whole concepts so that when I show my solving examples, you'll be able to understand. They gave us this E, right? Of an antenna, it's an oblique incidence, right? Because it is moving at an angle. It's not just in one direction, but in what? You can see that it is in this direction, it's in this direction, reflecting back in this direction. So they ask us to calculate beta 1. How do we calculate beta 1? That's just by doing what? The magnitude of this square, the magnitude of this square. You take the square root, you are going to get our beta 1. As simple as that. The next one is an entity is upon a soil surface, right? A soil surface, you get the beta 2. What is the answer for beta 2? You already know beta 1, right? What's the answer for beta 2? We don't know the answer. It is 2 pi over what? Over mu. Effective, in this case, we are going to consider the effective wavelength. How do we get the effective wavelength? That is, of course, considering the wavelength at the soil. That is taking the wavelength C is equal to f lambda divided by epsilon r. Then you are going to calculate, you are going to get our effective wavelength. So our beta 2 will now be equals to what? Our beta 2 is now equals to 2 pi over wavelength. When it is equals to 2 pi over wavelength, it's going to give us this in rad per meter. Then the incidence wave. Incidence wave is going to be what? We are going to calculate the incidence wave is going to be the magnitude of along the x axis divided by, you take the theta is equals to what? The magnitude along the x axis and then the magnitude along the z over the magnitude along the z. Don't forget vertical over horizontal. From there, we are going to get our incident angle in theta. They now ask us to get the expression for the total electric field in air and in the soil. You are going to get it separately. The electric field in air, this is the air interface, that's the medium 1. Of course, we will be able to get this electric field, the incident one, and then the reflected one. You are going to add in the electric field in the incident wave and that of the what? That of the reflected wave. Then you are going, that will give us the total electric field along medium 1. However, in medium 2, it was transmitted. So you are going to get the transmitted electric field here. That's just that about that. That's it. So the last one asks us to get what? They only ask us to get the electric field. They do not ask us to get the magnetic field. If they ask us to get the magnetic field, you are just going to use our formula. Our formula is what? Ke over wave impedance eta. Then you calculate that of this, add it to that of this. That's going to be H in me as medium 1. You get the transmitted one at this end too. That will be what? That will be H in the second medium. That is that about the next one. They also get the average power density carried by the wave traveling. The average power density that half S times H conjugate. It means that we are not going to make use of the H conjugate. It means we are going to get our H, the exactly as explained the other time. Then you are going to multiply it by what? The unit vector of the, and what's going to be the unit vector? It's going to be in x-axis and z-axis. Okay, you're going to assume that the distance is in positive direction. Then you're going to take the x and then az. You're going to multiply it by what? By the unit vector of this. Then you divide it by the what? By the wave impedance. As simple as that. So after getting h, you're not going to multiply the answer for h by e. When you multiply it by e, you divide it by half. That's the average wave density traveling in the soil. Simple as that. In the soil, it means our eta is going to be what? Is it going to be in the first medium or our eta in the second medium? In the second medium, because they ask us to find it in the soil, it means that the answer is going to be what? Mu naught over square root of epsilon r. And what is mu naught? That's 120 pi. That is 377 divided by square root of epsilon r. So we can get our epsilon r from beta. So from our beta given here, we can get our epsilon r. So it means you should be very careful while calculating the magnetic field. Now let me show the calculation of it as simple as it. The last calculation of it is, and then I forgot to explain that if you don't want to calculate H, of course, we already know from our elementary formula that the power is average power. This is equals to half V square over R. V is like E in this case, E square over R, or R, that is resistance, right? That's what limits the flow of electric current. So in this case, that's our wave impedance. Of course, it obstructs the movement of electric wave. So in that case, you are going to replace R by eta. We are going to replace V by E. So you can use it without calculating our H. So that's how to actually go about it, as simple as it is. Where did I start? Okay, now question 11, the last question. So you take the distance of the two, then you are going to arrive at our beta 1. You cannot get our beta 2 because it is in soil. Because it is in soil, we have to calculate the what effective lambda 2 for it to be 2 pi over beta. So effective lambda is 2 pi over beta 1. We calculate it from beta 1. That's that of the mu naught, of that of the free space. When we divide it by epsilon, when divided by epsilon r, we are going to arrive at the effective wavelength. The effective wavelength is going to be used to calculate our beta. That's how we arrive at this answer. The next one is we also calculate the incidence angle. The incidence angle, this is the angle along what from the first medium. We are going to calculate what. How do you calculate the incidence angle? That's taking the arctan of what x over z. So we're going to take the angle of x over z. Then the magnitude of x is mu. Theta is pi. The magnitude of this is this. Then you're going to arrive at our answer to be 2 points in degree. The next one, they ask us to calculate what? The electric field in air. We are going to calculate that of in air. In air, which is in free space, we have two electric field. The one that incidents on this and the one that reflects back. We are going to add the two together to get our total electric field. So that's in oblique. That's the incidence one, and then the reflected one rather, the reflected one, the one that goes back. So that was what we were able to get at this. And then for us to get that of the reflected one, we have to calculate the reflected coefficient, which is given by this formula. When we get the reflected coefficient, we are going to multiply it by the magnitude of that of this, multiply it by this. Then we are able to arrive at the reflected E, the incident E, this is. That's what gives us the what? That's what gives us the total electric field in air. Now we are going to that in exponential, because they are also to find it in instantaneous form. Of course, we can leave it in instantaneous form. Of course, that's just by introducing you. Since our question is already in instantaneous form, it's in instantaneous form, it is very wise to leave our answer in instantaneous form. So in volts per meter. So now in the second medium, that is in air, we're just going to use only one electric field, which is what? Which is the transmitted electric field. And we cannot get transmitted electric field without considering what? The transmission coefficient. Our transmission coefficient is given by what? One add 1 plus our what? Deflection coefficient. That's our transmission coefficient. From there, we can use our Snell's law to get them. Of course, to get our theta t, because our theta t is expedient, is very important when calculating a transmission coefficient. Then we can use that to calculate the coefficient. Then we can, from there, we can get our magnitude of the transmission coefficient, which is equals to E naught I, which was given E naught I was given to be 150, right? Multiplied by the transmission coefficient. Transmission coefficient is given to be 0.6. No, it was calculated to be 0.645 here. So we can get it from to be E there. So the last one is of course, now change it to what? We change to instantaneous form. When you change to instantaneous form, because our question was given in instantaneous form, you leave the answer in volts per meter. The last question asks us to calculate the power density carried by the wave. The power density carried by the wave, of course, that's equals to half times what? The electric field multiply, that's cross product of magnetic field conjugate. But when you don't want to do it in such a way, you can say half E square over what? Over eta, because we already know that half V square over R, that's our power. So when you do that, you are going to arrive at our final answer, which is what? Watts per meter square. So that is that about that. In short, the whole end chapter problem. This is just the easiest way of finding the end chapter problem without going through a lot. I hope this video helps a lot. Thank you so much. Okay, thank you. We stop the recording.